So today we're going to be talking about negative feedback amplifiers. And this is going to be gross at first, for sure. Just giving you fair warning. So we're going to analyze a simple circuit, one that you have actually analyzed before, way back in circuits one. This is a simple inverting amplifier. So our circuit that we're interested in is going to look something like this. We have our op amp. I'm going to put the inverting input terminal on top. Because we're dealing with negative feedback, we are going to tie our inverting input terminal to our output terminal, in this case using a resistor, where this resistor is going to be R2. I am going to ground my non-inverting input terminal. So this is V plus, this is V minus, this is V out. And then I'm going to have a resistance R1 between my input signal V in and the inverting input terminal. We're going to work this as a numerical example. So I'm going to give you guys some parameters for this particular op amp. Let's say that the resistance R1 is 5 kilo ohms, and our bias resistance R2 is 10 kilo ohms. Our internal resistance of our op amp, let's say that it's 1 mega ohm, and our internal output resistance is 100 ohms. Our open loop voltage gain, AVOL, is going to be 100,000 or 10 to the 5 volts per volt. And our input voltage, as it were, in this case, we'll make things simple and we'll just do a simple 1 volt DC input voltage. Realistically, I just want to clarify something here. Negative feedback amplifiers aren't really used to amplify DC signals too much because that's really wildly boring. So negative feedback amplifiers are used in what's called analog signal processing. The name op amp is actually comes from the fact that in a negative feedback configuration, operational amplifiers are used to perform mathematical operations on input signals. So while we're looking at this in a DC context to kind of figure some things out, realistically, their application is more with time varying signals. So I just wanted to make that very, very clear. I want us to determine the following quantities, some of which we are familiar with and others of which will require a little bit of explanation, okay? So the first thing that I want us to find is simply the output voltage, okay? Nothing really difficult about that. We're just going to wind up writing some KCL expressions, setting up a system of equations, and solving for V out like we've done previously. The next thing that I want us to find is AVCL. So this is the closed loop voltage gain, and it effectively represents the voltage gain of the system as a whole, right? So our open loop voltage gain is the voltage gain of the op amp as an open loop individual unit. And our closed loop voltage gain takes into account the feedback resistance network and all of that kind of good stuff as well. Okay. So this closed loop voltage gain is just the ratio of the output voltage of our system to the input voltage of our system. I also want us to find our differential voltage VD. This quantity doesn't really get used a lot. I just want us to make an observation about it, which is why I'm asking us to find it. I want us to find the input resistance of the system. I'm using a lowercase r here to denote that it's different than the uppercase R input resistance of the op amp itself. We could also call this like the closed loop input resistance or something like that. So just as a quick explanation, our input resistance for a system, if we had a black box system, where the input side of things is the left-hand side and the output side of things is on the right-hand side, then our input resistance for our system, let's say that we excite it with some sort of source over here, is just going to be the ratio of the voltage across the input terminals divided by the current flowing into the input terminals with the output terminals open circuited. Okay. I'm actually going to move this picture down a smidge. So this is how we're going to find Rn. And then I also want us to find the output resistance of the system, where doing something similar to the input resistance, we might apply our excitation source to the outputs of the system. So we excite it from this side, the output side, determine the ratio of our test voltage to our test current, and our input signal is turned off or short circuited in this case, since it's a voltage. So this is how we're going to find R out. Okay. So let's draw the practical op amp model representation of our circuit of interest here, right? So I'm going to start with my op amp as I usually do. I'm going to choose to put my inverting input terminal on top, and that is just to help me with drawing the feedback, okay? So down here, we are going to have our non-inverting input terminal. Up here is going to be our inverting input terminal, and our differential voltage VD is now going to be positive polarity on the bottom, since it's always defined such that the positive polarity terminal is at the non-inverting input. Here's our resistance Rn, which is 1 mega ohm. Here I have AVOL times VD. Here's my output resistance, sorry, which this has a value of 100 ohms. Our output voltage is the open circuit output voltage here because we don't have any load resistance to speak of. All right, so now let's make our external connections. So the first one that we can make, let me choose to represent ground right here. The first one that we can make is we know that our non-inverting input terminal is connected directly to ground, just to verify up here. That's what that ground connection right there is all about. So I can simply short this between the inverting input terminal and ground. I have that 5 kilo ohm resistor in series with my 1 volt source. So let's do that over here. And now I have my feedback loop, which is my 10 kilo ohm resistor connected between my inverting input terminal and my output terminal, like so. All right, so this is the circuit that we're going to be analyzing to find all of our different quantities. So how we are going to approach this is we're going to wind up applying Kirchhoff's current law at the inverting input terminal, adding these 3 currents together. Then we're going to wind up having to apply Kirchhoff's current law at the output terminal, adding these 2 currents together. We're going to wind up with a system of equations that we can solve for our different voltages. I guess realistically, we need the third one. No, we don't need the third one because V plus is by definition 0 volts. Okay. So let's start with KCL at the inverting input node. So the current that's flowing to the left and then down through the 5 kilo ohm resistor is going to look like the nodal voltage V minus 1 volt over 5 kilo ohms. Then I'm going to have my current that's flowing up through the 10 kilo ohm resistor. So that's going to look like V minus V out over 10 kilo ohms. And lastly, I have the voltage flowing to the right through our 1 mega ohm input resistance, which is going to be V minus V plus over 1 mega ohms. But since V plus is tied directly to ground, we're just going to call that V minus over 1 mega ohm. And so we can see pretty easily by applying Kirchhoff's current law here that we have 2 unknown quantities. So we're going to need at least 1 more equation. And that second equation is going to come from applying Kirchhoff's current law at the output node, which I can sneak that in over here, I believe. So for KCL at our output node, starting with the current on the flowing to the left, we are going to have V out, excuse me, minus our open loop voltage gain times our differential voltage. What's our differential voltage for this particular configuration. I'm not looking for it like a number because we can't get that yet, but in terms of our nodal voltages, I guess. Negative V minus, right? Because it'll be V plus minus V minus, and V plus is 0, so negative V minus. So this is actually going to look like V out plus AVOL times that nodal voltage V minus over 100 ohms. And then we're going to have V out minus V minus over 10 kilo ohms is equal to 0. And we now have a simple 2-equation, 2-unknown system that we could solve. Okay. I'm not going to make you guys throw this in your calculator or anything like that. I've already got it solved. So we can go from there. And what we find when we solve this system simultaneously is that our voltage V minus comes out to be 20.199 microvolts. How does that compare to our input voltage? Really, really small, right? So one of the characteristics of negative feedback in particular is that it's going to make our differential voltage very close to 0. Okay. Our output voltage is going to come out to be, and I'm keeping track of way more decimal points than I normally would here, negative 1.9999392 volts. Very close to 2, or negative 2, but I don't want to call it exactly negative 2. So we have effectively answered part A already. Okay. So now let's take a stab at part B, right? So our closed loop voltage gain, AVCL, is just V out divided by V in. And wouldn't you know it, I chose V in to be exactly 1 volt so that our closed loop voltage gain is just V out divided by 1, or negative 1.9999392 volts per volt. This guy right here is a quantity that's more representative of the system as a whole because it's not dependent on what input voltage we put in, right? So that we're going to get that voltage gain kind of regardless. So that's a pretty interesting thing. In as much as our open loop voltage gain for our op amp is 100,000. By putting these resistors in a negative feedback configuration, our closed loop voltage gain is pretty close to 2 in magnitude. Okay. Now, I haven't explained this yet. I don't remember, but I don't think I touched on it. But the open loop voltage gain of a op amp circuit isn't necessarily a fixed quantity. And let me explain explicitly what I mean by that. If I were to get a package of, let's say, 10 op amps made during the exact same fabrication run, the average value of those would be what's on the data sheet. But the value of each individual op amp's open loop voltage gain is going to vary some amount. On that data sheet I showed you guys, the typical value or the average value was 200,000, but I think it said something, or 200 volts per millivolt. But the minimum value that they have observed is 75 volts per millivolt, which is appreciably different, right? So the open loop voltage gain isn't a quantity that we can just inherently rely on. Negative feedback used in this way is providing us with a reliable, repeatable, finite voltage gain. That's one of the reasons that it's used. We can say, depending on the ratio of the resistors and all of that kind of stuff we use, I want my voltage gain to be X, and the resistive network provides that. So right now we have a voltage gain of extraordinarily close to -2. Notice that the ratio of our external resistors, 10 kiloohms divided by 5 kiloohms, is approximately 2. That's where that value of really, really close to 2 comes from, those resistors. The larger that my open loop voltage gain is, the closer those resistors will be to providing all of the closed loop voltage gain. That's another property of negative feedback. All right, our differential voltage, VD, we found earlier to be negative V minus when we were talking about how to put it into our KCL expressions. So that means that this is simply negative 20.199 microvolts. So now let's talk about how to find the answer to part D, our system input resistance. Okay. So if we were to treat the 1 volt source that we applied here as our test source, so this is our voltage, effectively Vx, the current that's leaving the positive polarity terminal of that voltage source is our test current, and the ratio of that voltage to that current is the input resistance of the system. I think we have enough information to find that current pretty easily, right? Because we can just use good old Ohm's law. So that current Ix is just going to be 1 volt minus V minus divided by 5 kiloohms. So this is going to be, let me write it like this, Vx over Ix. We know that Vx is 1 volt. Ix is 1 volt minus 20.199 microvolts divided by our 5 kilo ohm resistor. And we wind up getting an input resistance of 5,000.100997 ohms. Incredibly close to the 5 kilo ohm resistor we put in front of that test source. Right? Also another consequence of negative feedback. For our output resistance, that's going to be a little bit trickier. Okay. So if we look at this original diagram for finding R out, I described it as we apply a test source at the output terminals of the op amp and find the resistance from that. What does that remind you of? Exactly right. Even down to the fact that we are turning off our input voltage source, right? Because when you're finding the Thevenin equivalent resistance of a network containing a dependent source, we needed to make sure that we were looking at a dead network, right? So we could go that route, and there's nothing particularly wrong with that route. However, there's an alternative method for finding the Thevenin equivalent resistance, which I believe you guys are familiar with because I asked you to do it on homework set number 1. And that is simply to take the ratio of the Thevenin voltage to the Norton current. Well, as it turns out, with my output terminals open circuited, V out is my Thevenin voltage. So realistically, I could just reanalyze the circuit with my output shorted to find my Norton current and take the ratio of those two quantities as opposed to looking at the entire system backwards. Either way works. It's a little bit less work to find the Norton current here because we already have the Thevenin voltage, so that's the route that I'm going to choose to do. Okay. So I'm going to redraw my circuit. One mega ohm plus V minus. Since we already know how things are connected, I'm going to go ahead and add things in here. Which is 100 ohms. And now I'm going to short my output terminals. And the current flowing through this short is my Norton current. The last thing I need to add is my feedback resistor up here. All right, so we can find the Norton current in a couple of different ways. Arguably here, we have 3 meshes if we wanted to go about the mesh analysis route, but I am not going to do that. Instead, what I'm going to do is I'm going to apply Kirchhoff's current law to find my Norton current. So effectively, I'm going to say that this current flowing in plus this current flowing in add together to form my Norton current, because it's going to be actually a little bit less work. So the first thing that I'm going to do is apply Kirchhoff's current law over here at the inverting input node, much like we did when we analyzed the circuit earlier. And what we should find now is that we have a 1 equation, 1 unknown system because our output voltage is forced to be 0 since we shorted it out, right? So we would have V minus minus 1 volt over 5 kiloohms plus V minus over 1 mega ohm plus V minus over 10 kiloohms is equal to 0. 1 equation, 1 unknown system. We would find that V minus in this case is 0.66 right, stylus. 445 volts. Using this piece of information and applying Kirchhoff's current law at our output node, we find that our Norton current is the current flowing in through the 10 kilo ohm resistor. So that's going to be V minus over 10 kilo ohms. Plus the current flowing in through the 100 ohm resistor, which is going to be 10 to the 5 times negative V minus over 100 ohms. And if we substitute in that value from V minus above, this comes out to be negative 664.45176 amps. So I want to be very clear about something here. If we were to short circuit the output terminal of an op amp, we would not see 665 amps flowing through it. That would literally make it explode. Okay. This is a mathematical thing here that we're doing, not a physical thing. So if we take the ratio of, so R out is going to be V Thevenin over I Norton, with the understanding that V Thevenin was the negative 1.9999392 volts divided by negative 664.45176 amps. We find that our output resistance 3.0085 milliohms. So the system input resistance went down appreciably, effectively based on the resistive network that we had connected. The output resistance also went down appreciably. Both of these are properties of, once again, negative feedback. Yes, Ethan. Milliohms. Okay, so this analysis isn't too incredibly difficult. At least it's not anything that you haven't seen before. I'm definitely agreeing that it is rather tedious, okay? So before we introduce the ideal op-amp model, let's talk a little bit about what the ideal behavior of an op-amp would be. Then we are going to apply it to that circuit and see if the results are similar. Okay. So in my first lecture, when we first started talking about op amps, I gave you guys a kind of generic circuit representation where we had some signal voltage, excuse me, as a function of time over here in series with some resistance. Then we had the input terminals of our amplifier network. So here's where Vn lives. We represented our amplifier network with the practical amplifier model. So here we have our input resistance. Over here we have a voltage source with our gain times our input resistance, or excuse me, input signal. Here's our out. And then across our output terminals, we had some load. RL like so. And the true output, as it were, of the system was that voltage drop across that load. Okay. And I believe I told you guys that ideally we would find that the voltage drop across our load is simply the voltage gain of our system times our signal voltage. I'm gonna make a little change here. I'm gonna call this AV, AVOL, and I'm gonna call this guy AVCL, even though we don't necessarily have a feedback loop here, we're gonna choose to represent it like that. So what I'm trying to suss out from this statement is what the parameters R in, R out, and AVOL need to be in order to make this true, okay? Because that would mean that we have the ideal behavior. Our output voltage, V load, is literally just a scaled version of our input signal voltage, V sig. So, in order for this to be true, we need to look at a couple of things. So let's look on the output side first, okay? So we know that our open loop gain here is providing the scaling factor in some sense, right? So my question to you guys is, how do we make sure that this voltage V load here is the exact same as this voltage AVOL times VN here? What does the value of the resistor R out need to be to force those two voltages to be the same thing? Or zero, yeah. So we would need R out to equal 0 ohms for ideal behavior, okay? I agree with that wholeheartedly. So now we need to suss out what it's going to take to make V sig and Vn the exact same voltage. Or what value must Rn have to force that to be true? We're trying to make Vn of t be exactly V sig of t. So if Rn were 0, Vn would be 0. Much, much bigger, like infinity, an open circuit, right? So in an ideal op amp, the input resistance is infinitely large and the output resistance is infinitely small, or 0, okay? That will make Vsig equal to Vn and Vload equal to AVOL times Vn. I mentioned a little while ago that our open loop voltage gain needs to be as large as it possibly can in order for our resistor network to establish what our voltage gain for the system is. And so I'm just going to go ahead and reiterate that here by saying in an ideal case, our open loop voltage gain would be infinity. So, sorry, my allergies are bothering me this morning. Let's redraw our circuit and analyze it under these constraints. Okay. And I want to be clear here. We're going to do it this way exactly one time, and then I'm going to show you an easier way to do it, which is literally what we were doing in circuits one. So I'm not expecting you to have to replicate this. I'm just pointing out a couple of things. And it's actually going to show you where the ideal op-amp rules come from. So our circuit from our prior example is this, where we have an infinitely large resistor here. Here's V plus, V minus. We know that this is shorted. This is a 5 kilo ohm resistor. This is our 1 volt source. Over here, we have our infinite voltage gain multiplied by our differential voltage VD, where this is our differential voltage VD. Here we have a 0 ohm resistor. Here we have our 10 kilo ohm resistor. All right, so we're going to look at this in a slightly different order than we did when we had finite valued resistors for everything, okay? So what I mean by that specifically is looking at this circuit, we should very easily be able to see that our output voltage is just infinity times our differential voltage, whatever our differential voltage happens to be, right? And I can say that because there's very obviously no voltage drop across our 0 ohm resistor because it's a 0 ohm resistor. So this voltage and this voltage literally have to be equal, okay? Now, you might be saying to yourself, well, this doesn't really help anything because effectively I have two unknown quantities here. But I can rearrange this to find out effectively what's inferred, okay? So my differential voltage must be V out divided by infinity, just by doing the math there, which means my differential voltage by definition has to be 0. What does that mean? Well, the voltage at our inverting input node, or excuse me, our non-inverting input node must be equal to the voltage at our inverting input node. This is our voltage constraint equation, and it's also one of our ideal op-amp rules. There can be no potential difference between the voltage at the inverting input terminal and the voltage at the non-inverting input terminal. That's literally where it comes from. Okay. We can also see something else that's pretty darn easy. this current or this current both have to be zero because there's an open circuit there. That's where our second ideal op-amp rule comes from. No current can flow into or out of the input terminals because the input resistance is infinitely large. Okay? So we know where those ideal op-amp rules came from. Now let's go through this and sort stuff out really quickly. So I'm just going to apply Kirchhoff's current law at the non-inverting input node. So add these two currents together, set them equal to zero, and we wind up getting, actually I was going to say V minus, but that's not even really true. It won't be V minus because V plus is zero, so this is also zero. So we'll have 0 minus 1 volt over 5 kiloohms. Plus 0 volts minus V out over 10 kiloohms is equal to 0. Solving this, we can find that V out is -2 volts, which means our closed loop voltage gain is -2 volts per volt, which is exactly what's given by negative R2 over R1. So let's look at our voltage gain here really quickly, and let's calculate the amount of error that was introduced by using an ideal op-amp model versus the practical op-amp model, right? So our error is going to be our voltage gain, practical minus our voltage gain ideal over our voltage gain practical times 100%. I'm doing this part from memory. So technically it might be supposed to be ideal minus practical. It'll just change the sign. The magnitude is really what I'm interested in the error anyway. So I'll just say, put absolute values around these and we'll call it a day. Okay. So that's going to look like -1.9999392 minus -2 all over -1.9999392 times 100%. So throwing that in my calculator, I got 0.003% error. So 0.003 of a percent error by using the ideal op-amp model. So what does this tell us? Well, effectively, it tells us that anytime we're dealing with a negative feedback op-amp circuit, we can just use the ideal model because the amount of error that's introduced by using the ideal model over the practical model is relatively insignificant. In your homework set for this material, I have given you op-amp parameters for effectively just terribly designed op-amps. So input resistance is low on the order of kiloohms. Output resistance is high on the order of hundreds of ohms to kiloohms. Open loop voltage gains might be low, and you'll still find that realistically, even with a very poorly designed op-amp circuit in a negative feedback configuration, you still only get like 2% error tops. Okay. So realistically, anytime you're dealing with a negative feedback op-amp circuit, you can just use the ideal op-amp rules and you'll be well within the ballpark of what you're expected to get in your practical circuit. So just because not all of you guys had me for circuits 1, let's look at applying the ideal op-amp rules really quickly, or at least how I like to do it to analyze circuits. And then we'll wrap this up in a tight 5 to 10 minutes and get out of here a little bit early today. So looking at that exact same circuit, instead of representing things with the practical op-amp model and then putting in the ideal parameters, we're going to apply this approach. Okay. Here's this should be a 10K. 5K, 1 volt, ground. And I'm going to write the ideal op-amp rules out here. So the first one is there can be no current flowing into or out of the input terminals of an ideal op-amp. And rule number 2 is there can be no potential difference between the input terminals of an ideal op-amp. Okay. So when I'm given a circuit like this, or literally any negative feedback circuit, here is my approach. First thing I do is I apply op-amp rule number 1 by simply stating explicitly there's no current flowing into the input terminals. Okay. Those currents must be 0 because of ideal op-amp rule number 1. The next thing I do is I find the voltage at my non-inverting input terminal. What is that voltage here? 0 volts. Then I apply ideal op-amp rule number 2, which tells me that the voltage at the inverting input terminal must also be 0 volts. And then I apply Kirchhoff's current law at the inverting input node, which is going to give me 0 volts minus 1 volt over 5 kiloohms plus 0 volts minus V out over 10 kiloohms is equal to 0, and solve for V out, which would simply in this case be negative 2 volts. That simple process can be used for literally any negative feedback op-amp circuit. So apply op-amp rule number 1, find the voltage at the non-inverting input node, apply op-amp rule number 2, apply KCL at the inverting input node, solve for V out. If you are not sure what type of negative feedback amplifier circuit we have, and we're going to talk about commonly used ones in our next class meeting, this process literally always works. So when in doubt, do this. For your homeworks, for your exam, all of that kind of good stuff, I will explicitly tell you for the ideal op-amp circuit shown below, etc., when I'm expecting you to use the ideal op-amp model. If I don't explicitly say it is an ideal op-amp circuit, I'm expecting you to use the practical model. Okay. So I'm trying to make the directions as clear as possible so that there's not a whole heck of a lot of ambiguity or anything. All right, I am done for today.